Hey, geometry, it's Tuesday, May 5th, and we're starting on chapter 9, page 572, section 9.1. So in lesson 4.8, that's a long time ago, you learned that a transformation moves or changes a figure in some way to produce a new figure called an image. Another name for the original figure is the pre-image. I like to call it the original figure. You can see that line segment PQ is blue, and we slid it on up to PQ. We took Q and we rose it up a little bit and slid it over to the right. We did the same thing to P. And as a result, we got an image that is exactly like the original, except it's slid up. That's called a translation. It's a type of transformation. And the other ones, of course, you remember the rotations and all that nonsense. Okay, so right now on this section, we're going to be doing mostly translations. Example 1, we've got a quadrilateral. It's blue. Do you see it? The blue is going to be the original, and the red is going to be the image. Original, of course, pre-image. All right, you'll notice that A on example 1, it does not have a prime, but the red one does. A prime, little, what do you call those? Asterisk or something, I don't know, not asterisks. Colon, semicolon, I don't know what it's called. Little tick mark up there. And the B in the blue is the original or the pre-image, and the V prime is what we call it. We call it the prime, is slid over to the right. Okay, so what is the translation? Well, every value X and Y gets slid as X plus 3, Y minus 1. So for every value of X, we're going to add 3. For every value of Y, we're going to subtract 1. It's very simple. X and Y. It says point A is -1, 2. Point A is -1, 2. Now, if we add 3 to that, we get A prime is positive 2. And if we subtract 1 from that, we're going to get 1. B prime, C prime, D prime. B, C, D. And the givens are -1, 5 and 4, 6, 4, 2. And this is the way you're going to organize your work, just like this. And you're going to give me some brand spanking new ordered pairs. And we're going to subtract 1. So from -1, we're going to add 3. So 3 minus 1 is 2, right? That's the same. Yeah. And 5 minus 1 is 4. And 4 plus 3 is 7. And 6 minus 1 is 5. We got 4 plus 3 is 7. And 2 minus 1 is 1. So what does it say they want us to do? Graph the image using the prime notation. First graph the original. Okay, so we're going to go ahead and just take this bad boy like that. We're going to graph, you can eyeball this stuff, come on. -1 and up 2. Boom. Point A. -1 up 5. -1 up 5. That's point B. C is 4 over 4 up 6. Over 4, so if that's back 1, then this 4 would be like over to here. Up 6. Be like that. Point C. And over 4 up 2. Over 4 up 2. is D. And then we're going to go ahead and make this other one red, just because. And it's going to be, A is going to go down to 2 over 2, up 1. We're going to call that A prime. I'm not going to put the ordered pairs in there. Over 2 up 4, B prime. Over 7 up 5, that's 4. And 7 would be all the way over here, up 5. And 7, 1. Over 7, up 1. And so the original one looks like this. And the translation looks like that. That's how you can do those kind of things. Isometry is top 573. It's where a transformation has congruence. If you look at the red triangle in example 2, you'll see that it's congruent to the blue triangle. And the reason you know that is because if you were to find the lengths of each of the sides, you could prove them congruent by side, side, side. All you have to do is use the distance formula. Okay, translation theorem 9.1. That's an isometry. Yeah, I don't know what that is. Forget the theorem. Vectors, page 574. You can see the vector FG, not GF on 574, because the G has the arrowhead. A vector is a quantity that has both direction and magnitude, which means size. So if you look at that green arrow, does it have size, length? Yes, it does. Does it have direction? Northeast? Yes, it does. Okay, how did you get from point F to point G? Well, you went 5 units to the right and 3 units up. Could you find the length of FG if you really wanted to? Could you do 5 squared plus 3 squared equals FG squared? And find the, with Pythagorean theorem, find the length of FG? Of course you can. The initial point is the one that does not have the arrowhead. The terminal point, end point, is G. It's the one that does have the arrowhead. Horizontal component and the vertical component. The component form of that vector, if you look at it, is 5, 3. So you could call it one of 3 things. You could call it vector FG, or you could call it vector FG. Well, that looks like ray FG. I know, but it's in this case a vector, a term for a vector. And then 5, 3. Those are all 3 ways of describing vector FG. That's called the component form. Because vector F5, 3, you go over 5 and up 3. So if this is your starting point, your initial point, and this is your end point, if you're going over 5 and up 3, the question is, if you're going to go from here up to your grandmother's house over here, there it is, could you go 5 blocks this way and then go 3 blocks that way and get there? Or could you just go diagonally like this and get there a shorter distance? Either way, you get there. So are you telling me for a vector that 5 plus 3 equals whatever that is? Yeah. When you consider direction. 5 to the east, 3 to the north, gets you this far northeast. I know 5 plus 3 is 8, but the length of that is not 8. It's used the Pythagorean theorem. So example 3, name the vector and write its component form. Well, the vector on example 3a is BC because B does not have an arrow and C does. So it's going in the direction of C. So the vector is BC and its component form would be, let's see, how far does it go on the x-axis? 1, 2, 3, 4, 5, 6, 7, 8, 9. So it goes over to the 9 to the right. So that's in a positive direction. And how far does it fall down in a negative direction? It falls down -2. So the vector is called BC. And its component form is over 9, down 2. Okay. The vector B is -8, 0. It goes -8 and it drops 0 vertically. So it goes 8 in the x-axis negatively, and then it does not drop or rise, either one. And that would be going from S to T. So we'll call that vector ST. That's in the component form. Example 4, we've got a triangle, and we want to translate that using the vector 5, -1. Well, that's real easy. And do they want us to draw it? I don't think so, but let's just go ahead and show you how easy this is. We've got A is 0, 3. B is 2, 4. And C is 1, 0. Okay, so we're going to translate those into an A prime, a B prime, and a C prime. And we're going to use the vector to do that. We're going to apply the vector to each one of those points. 5, -1. Can you see that this is exactly what we said at the beginning of this lesson? That we're taking every point x, comma, y, and we're translating it into x plus 5 and y minus 1. This is the same thing as this. That's the same thing as that. Different notation. We're talking about vectors. The vector applies to every one of those 3 points. So let's go ahead and do it. Apply a 5 to the 0 and you get a 5. Apply a -1 to the 3 and you get 3 minus 1 is 2. And that would be 7. And that would be 4 minus 1 is 3. And this would be 6 and -1. Now, does it want you to plot them? If you plot them, it'll look just like the picture on 574. The original triangle is ABC, and then the image in red is A prime, B prime, C prime, and you can see that I got those points correct. Okay, number 4, on top of 575, name the vector and write its component form. Well, the vector number 4 is RS, and the component form is over 5 up 0, so it's 5, 0. It looks just like an ordered pair, doesn't it? And number 5, the vector is 0, 3. And 6, the vector is -5, 2, with these little doodads like that to describe the vector, like that right there. Okay, in example 5, solve a multi-step problem. I think I'm going to save that for tomorrow's lesson. See you.